Hey everybody, it's Dan from SageMathTutoring.com, and I have another video where I'm helping a student of mine with their calculus homework. This is a college level student, and she has some pretty interesting calculus problems here that I'd like to just jump into and go over. So let's just get right to it. So find a cubic function in the form below that has a local maximum of 4 at -4 and a local minimum of 0 at 3. So here's what the cubic function looks like. You know, when you're trying to figure out, okay, it says find a cubic function, right? So that makes me think, okay, well, maybe it could be, A could be a multitude of numbers, B could be a multitude of numbers, C and D could also be a multitude of numbers. It's possible that there's only one cubic function that would satisfy this criteria also. But, you know, you might run into problems if you try to graph it. Like if you were to try to graph this scenario, we have a maximum value at 4, of 4 at -4. So that would be a maximum value here, we could say, like right around here. And according to them, they have a minimum value of 0 at 3, which would be like right there. So one might be tempted to just be like, okay, well, let's imagine the function kind of looks like that. Okay. And then you could be like, okay, well, clearly there's a double root here. So, you know, when you factor out the cubic function and set it equal to 0, if you factor this cubic function out, set it equal to 0, well, we have a double root there. So, you know, maybe there's something like x plus 3 and x plus 3, and then clearly this x value is -4, so this could be, you know, -5, so maybe this is over here x plus 5, and then you might be tempted to just multiply all of this across and you would end up with x cubed blah 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 blah, and then you might be tempted to just call it a day. But the problem is this. We know that this value, this y-intercept here, it has to be between 0 and 4. But the problem is this intercept corresponds with D. Okay, D is the y-intercept. And it can't be between 0 and 4 if this is the case, because you'd end up with 5 times 3, which is 15 times 3, which is 45. 45, you know, once you multiply all these three out, the constant's going to end up becoming 45, which of course is larger. So that means that A, B, and C over here have to be some crazy shenanigans, maybe some like crazy fraction. So unfortunately, we're going to have to use calculus, which probably should not be a surprise. We're going to have to use calculus. Now, the key insight, number one, is to realize that, you know, the maximum and minimum values of a graph are always going to be such that the slope of the graph in that moment, the instantaneous rate of change in that moment of a maximum, a local maximum, and a local minimum, the instantaneous rate of change happens to be 0. The slope of the graph just in that moment happens to be 0. So maybe the slope of the graph, like right here, would be something like, you know, maybe that's like 3/1 or something like that. Maybe the slope of the graph over here would be something like that, okay, which might be -3/1, right? But the slope right here, well, that is a perfectly horizontal slope called 0. All right, that's a key insight. So what does that mean for us when it comes to calculus? Well, if we were to take the derivative of this function, the derivative of this function is the function that would enable you to find the slope at a given x value. So we know that the slope of this function at -4 is 0. And we know the slope of this function at +3 is 0. Okay? The slope of this function at -4 is 0. And the slope of this function at 3 is 0 also. So if we were to take the derivative of this function and plug in -4, we would get 0. And if we were to take the derivative of this function and substitute in 3 for x, we would also get 0. Okay, so hopefully that makes sense to my students at least. So let's go ahead and just kind of see what happens when we take the derivative of f of x. Now, f of x is this. And when we take the derivative, we end up with this right here. We have 3ax squared plus 2bx plus c. And I'm already seeing that we're going to have to do a lot of like substitution basically, because the bottom line is we know, here's the derivative of f of x. And we'll start with this information. We know that the slope, that this derivative will equal 0 rather. This should equal 0 when x is -4. So let's kind of force that to happen since we know that that's true. So we end up with this substitution. And we're going to be detectives and just piece all of this together, basically by using a ton of substitution. Let's just get this over with. We're going to call this -8b plus c. And this becomes 0 equals 48a minus 8b plus c. Now, I'm just going to tell you, I can already foresee the usefulness of solving for c right now, because at the end of the day, we're going to want to solve for c, b, a, and d. C is like primed right now to be solved for, so I'm actually going to leave c on the right, and I trust my student to just understand that we have an 8b minus a 48a on the left. Okay, she could always pause the video. We're going to leave it at that for now. Okay, we know that c equals this. Now, I'm tempted to find out, okay, c equals this, but what else does c equal? And, well, one way of finding that out is to sort of rewrite the derivative off to the side, over here maybe. I'm just going to go ahead and rewrite it for now. And now we're going to work with the other, what was it? It was the minimum value. We're going to work with that now. Okay, so we have 2bx plus c right here. But now we're going to set this equal to 0. And we're going to ask ourselves, okay, well, what other x value would cause the slope to be 0? Well, apparently it's 3. Okay, so we're going to go ahead and plug in a 3 for x and find out what c equals. Okay, so we end up with 27a plus 6b plus c, and at that point c equals, we had b and then a, so we're going to do the same thing. So it's going to be negative 6b minus 27a. And then we could set, since c equals c, then we know for sure that negative 6b minus 27a equals 8b minus 48a. So do a little line here. And we could, of course, set these equal to each other. So we have 8b minus 48a equals negative 6b minus 27a. And we'll add 6b to both sides. That gives us 14b, and we could add 48a to both sides, and that gives us 21a. All right, so at this point, we're going to make the decision to... We'll make a the star of the show temporarily. So basically choose a variable to be the star of the show. We're going to choose a as the star of the show. What the heck do I mean by that? Basically, I mean we're going to solve for every variable in terms of a. So right now we're going to solve for b in terms of a. And I have a plan now of solving for c and d in terms of a also. Okay? So a equals a. B is about to equal something in terms of a. Then we're going to figure out what C is in terms of a. And then we're going to figure out what D is in terms of a. Okay, so A is the star of the show. So B in terms of A is just going to be a matter of dividing both sides by 14. And that gives you 3/2 A. Now, we can just simply choose one of these two. It really doesn't matter which one. We're going to choose this one, and I'm going to replace B with what we know it equals in terms of A, and find out what C is in terms of A. So we know that B is equal to 3/2 A. And -6 times 3/2, the -6 would turn into a -3, and the 2 would turn into a 1 because of that cancellation. So this becomes -9a minus 27a equals c. And you would discover that c therefore equals -36a. So we know for sure in the blue box that b equals 3/2 a. We know for sure in this blue box that c equals -36a. And we now have the power to figure out what d equals in terms of a. So we're going to do that right now. So we're going to figure out what d equals in terms of a by rewriting the original function. So here's the original function. It was ax cubed plus bx squared plus cx plus d. So we could figure out what d equals in terms of a. Let's see. So ax cubed plus b is 3/2 a, so that's going to be 3/2 a x squared plus c is -36a, so we'll actually say -36a x plus d, and that's what f of x equals. But we have the privilege of knowing that when x is, for example, -4, then y is 4, right? We also know that when x is 3, y is 0. I'd rather work with that second part, according to the original situation. And this is kind of small. Let's look at it right here. Just this information. Right here, we know that when x is -4, y is 4 in the original function, and we also know that when x is +3, y is 0 in the original function. So we will put that off to the side for now. I think I moved that, right? So I'd rather work with the latter of the two pieces of information, because any opportunity to work with a 0, I'll take. So y is 0 when x is 3, so we could just kind of write the whole function only with empty parentheses. and we'll see what happens here. It's getting a little crowded with all this other stuff, so I'm going to move some things around right now. I think just moving this up would be helpful. So we're going to move this guy up, and we are keeping in mind that what we're doing now is based on the fact that we figured out what B is in terms of A. We figured out what C is in terms of A. Here they are. And we're taking advantage of the fact that we know that there's a minimum of 0 when x is 3. So we're going to go ahead and plug in 3 here. And the reason for that is because now we want to figure out what D is in terms of A. And we're about to do that. So this becomes, as a result, 9a. Actually 27a right there, right? Because that's cubed. 27a. This is a 9, and we'd end up with, unfortunately, 27 over 2a over here. It's unfortunate. So it's an ugly number, but we're going to keep everything in the fraction form. This is going to be negative 108a. So that's negative 108a plus d. And once again, we want to figure out what d equals in terms of a. So I'm going to leave d on the right-hand side right now. And in a sense, send all the other terms to the other side. We're going to subtract 27a from both sides. We're going to subtract, 27 over 2a, and we're going to add 108a, and I'm just going to do that right now all at once, trusting that my student knows how to do that. So that would be 135 over 2a. And I'm going to wrap a blue box around that also. So what we have on our hands, just in general, is the following facts. We know for sure that B equals 3 halves A, C equals negative 36A, and D equals 135 over 2A. Okay. So again, for my student at home, I'm really hoping I'm not making any careless mistakes. There's always that possibility. But the general principle is what's important, and that is to solve for one variable. We could say, or solve for all variables in terms of one variable, and choose one variable to be the star of the show. In this case, it's A. So we're solving for B in terms of A, we're solving for C in terms of A, and we're solving for D in terms of A. That's really the first step. Now the question is, what do we do now? Well, once you've done that, once you've followed that process of picking a variable and solving in terms of that variable with regards to the other variables, A, B, and C. And actually, I should really not be calling these variables because it's highly likely that they are, well, it's definitely true that they're just a number, right? They're not a variable. X is really the variable. But we'll just call it A, B, and C. So we solved for D in terms of A. We solved for B in terms of A. We solved for C in terms of A. And we also worked with this information here where we know that when it comes to the original function, when x is 3, y is 0. But we could also take advantage of the fact now that when x is negative 4, let me blow this up. We could also take advantage of the fact that when x is negative 4, y is 4. And believe it or not, now that we kind of solved for every other letter in terms of A, we could figure out what A is now by using that other point. Okay, so here's what I mean by that. Rewrite the function once again. I'm just going to rewrite it right here. So ax cubed plus b x squared plus c x plus d. But guess what? We now know what all of these are in terms of a, so I'm going to actually rewrite all of these in terms of a. So we know for sure that a is just a, so that's that. We have our 3/2 a right here. We know that c is equal to negative 36a, so we're going to rewrite that. But now we have d, don't we? We have d plus 135 over 2a. And that's what f of x equals. You know what else we know? We totally also know, once again, that in the original function, when x is negative 4, y is 4. That's what we know. We know that for sure. So let's write that down. We know that when x is negative 4, y is 4. So why not just write that? Now, I'll do the empty parentheses. My student knows that that's the way that I like to do things. I'm just going to write empty parentheses for now. I'll fill it in with that negative 4 in a moment, but not yet. So this becomes 135 over 2a. Okay, filling it in with negative 4. I like to do color coding. That's really the reason. And to be super careful with parentheses as well. Because, you know, we're squaring this one and we're not squaring this one. So it's like that. So on the next line, we end up with 4 equals, well, negative 4 cubed is 64, so that's going to be negative 64, actually. Negative 64. Okay. Negative 4 squared is 16. That's going to be plus 24a, unless I made a careless mistake. This negative 4 times negative 36, well, we know it's going to be positive, and it's going to be 4 times 36, which is 144. A. And then we have plus 135 over 2. A. Okay, so looks like we're going to have to combine all of these like terms. I don't want to deal with this too, so I don't know, maybe that's just me. So I'm going to multiply everything by 2, you know, multiplying both sides of the equation by 2. So that's going to give me 8 equals negative 128a plus 48a plus 288. A plus 135. I feel, you know, more comfortable just combining these like terms, so I'm going to do that right now. So that becomes 343. 343a equals 8. So we then have a equals 8 over 343. So again, unless I made a careless mistake, it's official. We just solved for one of those letters, right? And once you do that, the rest is like a house of cards that just like tumbles, you know? That's the right metaphor. But once you do that, it's like, all right, well, great. Let's look at all the blue boxes, you know? It's like we know what A is now, so let's solve for C, let's solve for B, let's solve for D, you know? So let's do that. So we'll start with B, you know, why not? B equals 3/2 A. Well, it's like we know for sure that A is this crazy fraction right here. This is a crazy fraction. Welcome to calculus, where when you attempt to solve these problems, you are not quite sure if you've screwed up somewhere along the way, because the numbers you end up working with are ridiculous. Prior to calculus, the numbers are typically kind of clean and nice, you know. Now we have to deal with numbers like this. 3 and 343, it's like, okay, is 343 divisible by 3? It's not. So that's kind of a problem. We can't do a cross cancellation, but we couldn't do a cross cancellation here. So I'm happy leaving it in this like fraction form. So this becomes 12 over 343. I'm happy just leaving it that way. I hope the computer and or the teacher is happy with it. So anytime we solve for an actual letter, let's wrap it up in a yellow box. Okay, focusing now on, we just solved for B, literally. Let's solve for C. So C is negative 36 times whatever the heck A was. A is 8 over 343. So here we are. Not divisible by 3, also not even, not divisible by 9. By the way, how do I know it's not divisible by 3 or 9? Well, when you add 3 plus 4, that's 7, plus another 3, that's 10. 10 itself is not divisible by 3 or 9. That's a trick of the trade. Therefore, this is not divisible by 3 or 9. 343 is not divisible by 3 over 9. So, 3 and 9, that's a nice factor of negative 36. So, unfortunately, we're kind of stuck with this scenario. What is negative 36 times 8, though? That's the question. That is negative 288. Negative 288. And that equals C. Yellow box for that one. Okay. And we'll do a little yellow box around that. And great. Now we have to look at D, right? Where's D? D is right here, right? So let's find out what is going on with D. Seeing as how A is 8 over 343, well, D, therefore, is going to equal 135 over 2 times what? 8 over 343. So once again, we have a nice cross cancellation there. 135 times 4 over 343, working that out now gives us 540 over 343. Yellow box for that one. So let's kind of back up and get the big picture. Focusing on the yellow boxes, we now know what A is. It's 8 over 343. We figured out what B is. It's 12 over 343. We just figured out what C is. It's negative 288. And we just figured out what D is. That's 540 over 343. We also know that the original function is of this form, where it's like A x cubed, b x squared, so on. So I'm pretty sure my student knows where this is going. All we have to do now is literally write the original function, only with A, B, and C, and D where it belongs. All right, so I say we go ahead and just do that now, actually. And then we'll review like what was involved, So we're going to do that now, keeping all the yellow boxes in view. Original function about to get rewritten. F of x equals, and again I'm going to write empty parentheses, something x cubed plus something else x squared plus something else x plus something. Well, what is that something, or those some things? That will be, A is 8 over 343, 8 over 343. B turned out to be 12 over 343. C turned out to be negative 288. We'll work with that in a moment. D turned out to be 540 over 343. And I'm going to rewrite it now that in such a way that would take into account this negative 288, and then we're going to call it a day. All right. So this ends up becoming that fraction coefficient plus that fraction coefficient. We'll just say minus 288x plus this fractional constant. Okay, so this is all under the assumption that I didn't make any careless mistakes when it came to combining like terms and so on, but at the end of the day, this is the answer, assuming no careless mistakes. Let's go over the principles of how I solved this. And in order to do that, let's actually get clear about the original problem. Right, well, we'll leave this here. That's fine. What was the original problem? Let's kind of blow up. I feel like I have to be a cinematographer in addition to a math tutor when I do this stuff. So, zooming in on this, find a cubic function in the form below that has a local maximum value of negative 4 and a minimum value of 0 to 3. So basically what I had done is I had reminded us that graphically this really looks something like that, with the realization that the maximum value right here, basically when x is negative 4, y is positive 4. When x is 3, y is 0. Alright? When x is negative 4, y is positive 4, and that happens to be this point. When x is 3, y is 0. That happens to be this point. Furthermore, when x is negative 4, y is 4, sure, but we know that the slope of the graph at that moment is 0, also known as the derivative of the function when x is negative 4 is literally equal to 0. We also know that this is a local minimum, so we know that the derivative of the function when x is positive 3 is literally equal to 0 because the slope of this graph when x is 3 is equal to 0. As a reminder, what does the derivative do? When you take the derivative of the original function, it gives you a new equation that helps you find the slope, depending, the instantaneous slope of the original graph, depending on what x value you're looking at. Okay. So we took into account that insight, and we remembered, therefore, that, okay, we could use that information to figure out what the letters A, B, C, and D are by finding the derivative of the function here. Let's blow this up. We found the derivative of the original function. We got 3a, blah, 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 blah. And then what we did is we solved for c in terms of the other two variables. And we also, when we did that by taking into account the fact that when x is negative 4, the slope is 0, and we got c equals all of that stuff, right? And we worked with the derivative again over here, but we used the other 2 points when x is 3, y equals 0, because when x is 3, we know that we have a slope of 0, and we got another equation for c. So that's a good rule of thumb, kind of solve for c here, because at that point, that's when you're ready to set this equation equal to this equation. And at that point, you can finally solve for b in terms of a. So you can pick the star of the show after that. All right. We solved for b in terms of a. And once we did that, we plugged in, negative 3/2 a into this guy, and we solved for c in terms of a. I did a color coding scenario where whenever we solved for a letter in terms of the star of the show letter, I wrap it up in blue. We solve for c in terms of a. And then at that point, we're able to go up here to the original function, actually, and plug in, this stuff. And what do? We picked one of the points where it's like f of x equals 0 when x is 3. We just kind of picked one of those points, right? We could have also used, we could have used 4 here and negative 4 here too, but we just so happen to choose the point 3, 0. And then we solved for d in terms of a, and we wrapped that in a blue box. So we have b in terms of a, c in terms of a, d in terms of a. Then what did we do? This came later. We then also worked with the original function again, only this time instead of writing d, we put in 135 over 2a because we had just discovered that, right? Now, only at that point were we able to work with the other point, negative 4, 4, which is certainly on the original function, right? Negative 4, 4. And then it was official. We were able to finally actually solve for a in that moment. Okay. And then once you found a, like I said before, the rest is a house of cards, right? I decided to do a color coding where we wrap that up in yellow. Anytime you actually solve for a, b, or c, or d, you wrap it up in yellow. And we already knew that b was equal to 3/2 a, so then we solved for b here, wrapped it up in yellow. We already had known that c was equal to negative 36a, so we solved for c, wrapped it up in yellow. We had already known that d was equal to 135 over 2a, so we solved for d and wrapped it up in yellow. And honestly, once you have a, b, and c, and d, all you have to do is refer to the original function, which obviously, is here, and then you just plug in a, b, c, and d, and then you're good to go. This should work. All right, so that's how you do the first problem. Okay, so before we move on to the next problem, I actually realized there was a slight careless mistake, and it has to do with c. Okay, so with regards to c, the careless mistake is the fact that the numerator is negative 288, but we still should have this denominator of 343 underneath. All right, so let me just write that. And the way that I know that I made a careless mistake, for the record, is because I plugged it into the calculator, like the final function, and it did not have the maximum, the local maximum, and the local minimum where I wanted them to be. So I had to kind of review everything and see where I made the careless mistake. So yes, c has a denominator of 343. That right there will definitely work. All right. Regardless, all of the principles are the same with regards to everything that I talked about. And just to be sort of thorough, I'm going to even write in a little 343 on the bottom right there. Okay, so hopefully that makes sense to my student. Hopefully that makes sense to those of you at home watching. And let's move on to the next problem. Okay, so the next problem is this. G of x equals integral blah blah blah, where f is the function whose graph is shown. Evaluate g of 0, g of 1, g of 2, g of 3, g of 6. So good job, my dear student, for getting g of 0. And let's look at, of course, what went wrong with these guys. So the integral of a function should give you the area under the curve of that function, or under the graph of that function. And so therefore, when we're calculating the integral from like x to 0, we want to calculate the area underneath this graph from x to 0. And I want to make clear, this is something that tripped me up last time. Let's see, so this graph should be right there too. That's not clear to me. I'm assuming that there is a little line there as part of the graph. So anyway, the reason why it's definitely true that g of 0 equals 0 is because g of 0 is to say the following. G of 0 is to say this. And the bottom line is, it doesn't even matter what like the function is or whatever. If you're calculating the area under the curve from 0 to 0, well, of course that's going to be 0, you know, because the range is 0 to 0. So there is no area under the curve from 0 to 0 because there is literally no graph between 0 and 0. Okay, if that makes any sense. Had you asked for 10 to 0, well, that would calculate the area under the curve all the way from x is 10 to 0. But if you're calculating the area under the curve from 0 to 0, that's just 0 to 0 right here, okay? So there's nothing there. There's nothing there. Anyway, hopefully that makes sense to my student. It's kind of a weird way of explaining it. I'm sure an animation would help with that. But moving on to the next one, g of 1. So that is most definitely to calculate g of 1, which looks like this. That's going to be this integral from 1 to 0. And that is taking note of this range right here. And that's why I was kind of insisting upon drawing this line. I'm pretty sure that since we're talking about this range right here from 1 to 0, we want to take into account that. Right, these two blocks, it looks like each block is a 1 by 1 block, so the area there should be 2 because we have two 1 by 1 blocks there. Right. Essentially, when you're calculating the area under the graph, you're really counting how many blocks you're dealing with. Okay, we're dealing with 2 blocks there, so the answer to that should be 2. I'll kind of keep a compilation of answers here. G of 0 is 0. G of 1 equals 2 because the area under the curve there is 2. Let's figure out what is a G of 2, G of 3, and G of 6. So we're going to figure those out now. And G of 1, let's see, that should be 2. G of 2, that takes into account the area under the curve from 2 all the way here. Okay, so we definitely know for sure that we have already these 2 blocks. All right, so 2 for the records right there. So we already have these 2 blocks. We're also going to have these 2 blocks. I'm going to kind of draw an X through those. So that's a total of 4 blocks, but we also have this little triangle to contend with. Now the bottom line is this triangle, this little triangle right here, which I will shade in yellow. This yellow triangle is half of these 2 blocks, right? if we were to take into account these two entire blocks. This little yellow triangle is half of that. So the area of this little yellow triangle is 1 because it's half of these two blocks. So we have 2 plus 2, which is 4, plus 1, which is 5. All right. So that is the reasoning process behind the answer of g of 2. G of 2 would be the area under the graph there, so that should be 5. Okay. I'm going to write that right now. G of 2 is 5 because the area under the curve in that range is 5. Okay. So moving on, looking at G of 3 now. G of 3 is asking for the area under this whole graph in between 3 and 0. So let's take a look at what's going on there. So taking into account this range now between 3 and 0, well, we had already discovered that this section plus this shaded triangle, we know that all of that stuff is 5. So from there to there, this black bracket right here, all of that's 5. So we need to take into account this kind of triangle right here, which I will denote in the red shading, because whatever the area of this red shaded triangle is, we're going to add that on top of the area that we already have, right? Because we already have 5. So the question is, what is the area of this red shaded triangle? Well, once again, really the fastest way, in my opinion, to figure out the area of these little triangles is to take into account the area of the rectangle that the triangle is a part of. And we have a rectangle, like a large vertical rectangle of 1, 2, 3, 4. This large vertical rectangle has an area of 4, so therefore half of that area would give us this red shaded triangle. So therefore the area of the red shaded triangle is 2. All right, so I hope that makes sense. So we're going to zoom out once again and take note of the fact that we already had that area of 5 represented by the black bracket, and we're adding on an extra area of 2 on top of that, namely through the red shaded triangle. So we're going to put 7 right now. There. Okay, now the question is, what is g of 6? In other words, what's the area of the curve all the way from 6 to 0, right? Now, let's keep in mind that the area from 3 to 0 is 7. I mean, we already just discovered that, basically. And I'm going to label that on the graph. I can already foresee that that's going to be helpful. In fact, we already have this like blue bracket that's just waiting for us to label it with a number of 7. So we know that everything above the x-axis here is 7, okay, including this red triangle right there. We're going to disregard this blue rectangle shape thing. Bottom line is, we know that all the way from 3 to 0, the area under the curve is 7. But now they're asking us for the area from 6 all the way to 0, right? That's what this means, from 6 all the way to 0. So I'm going to label 6 right here, and we are taking into account everything from 0 to 6. That's the question at this point. All right, that's the question at this point. In fact, I'll write a little question mark right here. Okay, that's a question mark right there. Now, we know that the area from 6 all the way to 0, well, it's definitely going to take into account 7, right? But now we have all of this stuff to contend with, right? And the bottom line is, this stuff is clearly under the x-axis, like this area of the graph, this section of the graph is under the x-axis. So the quote-unquote area under the graph is going to be negative. It's going to be the space between the graph and the x-axis, but it's going to be a negative number, okay? The integral from 3 to 0 was essentially the space between the graph and the x-axis, and it was a positive number. The quote-unquote integral between, in this range from, we could say, 6 to 3, well, that's once again going to be the space between the graph and the x-axis, but it's going to be a negative number. So in other words, it's going to be the area of the blocks in between the graph and the x-axis, but we're going to assign a negative number to it, all right? So my thought is, let's just calculate it visually. First of all, we definitely have an area of 2 here, right? We have these 2 blocks that are in between the graph and the x-axis. So we're going to take into account that area of 2. And then the question is, what is the area of this shaded triangle right here? And my student at home, I'm pretty sure, would understand, especially after me talking about all this stuff, that the area of this green shaded triangle is going to be half the area of this red square. Now, the area of this red square is clearly 4, so therefore the area of this green shaded triangle is going to be half of that, so that's going to be 2, right? So the area of this yellow, maybe we could make that a rectangle too. This yellow rectangle, the area of this yellow rectangle is 2, plus the area of this green shaded triangle is another 2, so that's going to be 4. Now, as I said before, it's like, sure, the area of the boxes between the graph and the x-axis is 4, but it's going to be a negative number because it's under the x-axis. So the area, therefore, is negative 4. So what that means is we have an area of a positive 7 here, denoted by the 7. So it's going to be 7 plus this negative 4 area. In fact, I will do in brackets calling that negative 4. So then at the end of the day, 7 plus this negative 4 is going to be 3. So when it comes to this question mark, that's going to equal 3. All right. The area under the curve, the area quote-unquote under the curve or under the graph, all the way from 6 to 0, ends up totaling to 3. So, therefore, we could write 3 right there. Okay? So hopefully that makes sense. Let's take a look at the next question. Okay, on what interval is g increasing? Well, that you can clearly see by the values that we just considered, right? I mean, g of 0 is 0, g of 1 is 2, so it's increasing so far, right? G of 2 is 5, g of 3 is 7, so it's increasing so far. But something happened after g of 3, right? And that's really the cutoff point. G of 3 is the cutoff point where it became official that G started decreasing, okay? Now, in case that's not clear, I think there's multiple ways of understanding what the hell we're even talking about, okay? I'm going to stick with the area filter, like the interpretive filter of considering the area, right? So for my student, I would just ask her to recognize that since g of x is an integral, and integrals give the area under the curve, right? G of x is an integral, so g of x represents the area under the curve of f, right? F is some function. And g of x gives the area under the curve of f. So you know that g of x is increasing in whatever range the area of the under the curve is increasing, right? You know g of x is increasing whenever the area under the curve is increasing, okay? So let's look at this graph. This is the graph of f. So we need to ask ourselves, okay, well, where is the area under the curve increasing? Well, when you consider from 0 to 1, I mean, it's clearly increased, you know? When it was at 0, the area under the curve was 0. When it was at 1, the area under the curve became 2, right? When we moved to this x value of 2, the area under the curve just increased to 5, right? From 2 to 0. From 0 to 3, the area under the curves increased, even though the slope, so don't get confused, even though the slope went down, when we moved from the x value of 2 to the x value of 3, well, the area under the curve increased. It went up to 7 in that moment. But in that moment, once we moved to 4, well, the area under the curve started to decrease a little bit, didn't it? Right? It started decreasing because all of a sudden we have this negative value of negative 1/2, right? So in that moment, even though the homework assignment didn't ask for it, you know, when we were at g of 3, the area under the curve was 7. But once we got to g of 4, that 7 just decreased by half. So we were at 6.5 in that moment. And then once we went to g of 5, the area under the curve decreased once again. In that case, it decreased by a total of 2. So we went from 7, and then we had to subtract 2. So the area under the curve at that point was actually 5. Okay. So anyway, this is the peak of the area under the curve. You know, here's the graph of f. The area under the curve was 2, then it was 5, then it was 7, and then it started decreasing at that point. Okay, so that's the way to understand it, in my opinion. Think of the integral function as the area under the curve. Think of it purely in that way, and you should be fine if you do that. So, looks like the teacher's giving this nice parentheses, which means it's like that interval notation. So we're looking at from 0 to 3. That should work. Okay, so where does g have a maximum value? Well, it has a maximum value at 3 for the same reasons that we just said, right? In case that's not clear, you can kind of see it with this information. When x is 3, when you're considering g of x and x is 3, that's when the quote-unquote y value is the largest, right? That's the maximum value right there. It's at 7. In other words, another way of interpreting this question is, where does g have a maximum value? They could say, at what x value is the area under the curve of f the largest? Okay, so I'll say that again. When you hear the question, where does g have a maximum value, another way of asking that question is, at what value of, we could say f is such that the area under the curve is the largest. Okay, and it was 3. It was in that moment. Okay, when x was 3, the area under the curve happened to be 7. And then it started going down after that. Okay, sketch a rough graph of g. Do this on paper. Your instructor may ask you to turn in this work. Okay, so let's sketch a rough draft. We're going to kind of utilize the values that we have. I mean, even if you're not quite sure how to do it just yet, you really can't go wrong by doing that, all right? Because we know for sure that all of these values are certainly on the graph, right? So Let's see, at g of 0, well, let me get clear about the range. The domain that we could consider is from 0 to 6. I'm comfortable with that. And the range that we could consider is from 0 to 7. I'm comfortable with that too. So 0 is going to be right there. We will have 6 here. And we shall have a range of 0 to 7, so we'll call this 6, nice perfect square, and then 7 would probably be about that, right? Let's get some in-between values. Why not? We'll have 3, cut that 6.5, cut this 6.5, and take it from there. So 1, 2, that's 4, that's 5. And why not? We'll do a 7 here, that's fine. 1, 2, we have 4, we have 5. Okay, so yeah, I think it's a decent idea to just rely on these, to be honest. So it's like, this is a sketch of G, so I'll write that this is G of X. And we definitely have a point here. G of 1 is 2, so that's right here. G of 2 is 5, so that's right here. G of 3 is 7, so that's right there. And let's just cut to the chase. We have G of 6 is 3, so that's going to be right here. Now, you could, since it's like a rough sketch, you could just connect the dots here. I feel like it might be a nicer idea to get clear on some other values. If for no other reason than to kiss the teacher's butt a little bit. So I'm going to do that. All right, now whether or not this is necessary, not exactly sure. But let's take into consideration G of 4 and G of 5 at least. I had mentioned those before, but let's actually write it down now. So we know for sure that at G of 3 we have 7. So in other words, the area under the curve here is 7. But then once we move to G of 6, we're subtracting. Once we move, to G of 4, we're subtracting 1/2 from 7. So 7 minus 1/2 is 6.5. So I'm going to write that. So once again, G of 3, we had an area under the curve of 7. But once we moved over 1 unit to G of 4, we're subtracting this little area, this half of a square right there that's underneath the red dot. And 7 turned into 6.5 in that moment. And then once we moved to G of 5, we moved to this moment, this x value. And what used to be a positive area of 7, now just we're subtracting 2 from it. So that becomes 5. So I'd like to just write that right there. So we know for sure that G of 4 is 5, so that's, or 6.5 I should say, so that's going to be like right there. And then G of 5 is 5. So I'm going to draw a dot here. I think that that's a better idea. When the teacher asks you to sketch the graph, it's like, could you get away with just graphing these points and playing connect the dots? Sure. But, get a little bit more accurate. G of 4, G of 5, those are sort of the quote-unquote missing values. So figure out what they are and then sketch the graph after that. Okay. And you can see that that gives a slightly more accurate depiction of what's happening. So I'm comfortable with that, unless I made a careless mistake as usual. That is how that works. So hopefully that's clear to my student. We covered everything. I don't think I missed anything there. Okay, so hopefully that's clear. Moving on. Okay, so g of x equals blah, 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 where f is the function whose graph is shown below. Yeah, it's going to be a similar situation, right? Similar process. So let's do this one. I think I'm going to move through this one a little bit more quickly, because since it's a very similar problem to the last one, I believe my student probably understands, you know, how to do it. Okay, but I'm still going to do it anyway. So here we go. So let's look closely at what is going on here. Okay, so g of 0, it's like, for the same reasons as before, the area under the curve from 0 to 0, well, that's most definitely going to be 0, right? So we don't have to talk much about that. And then they ask from g of 2, so that's going to be the area under the curve from 2 to 0. Okay, so let's just get clear about this right now. When you do these problems, you're going to want to ask yourself, what's the area of a single block? The area of a single block is 2 by 2, so that's going to be 4. Okay. Each of these little, I'll call them squares or blocks. Okay. I'll stick with block because it doesn't really look like a square. The area of each block is 4. No question about it. So we see this block being cut in half. So that's going to be like the area of this triangle right here. That's certainly going to be half of 4. So that's going to be 2. So therefore, g of 2 equals 2. Why? Because the area of that little triangle right there, from the range of 2, or from the domain of 2 to 0, is 2. So g of 2 is 2. All right, moving on. G of 4, what's that? Well, I'm already seeing the necessity of labeling this graph, to be honest. I'd rather get clear on what each of these are. That's 10. That's 14. So when they're asking for g of 4, that's the area under the red curve from 4 to 0. Well, this actually cancels out, doesn't it? Because when we take into account this triangle, which is we could say the area between the graph and the x-axis, well, this yellow triangle is, we could call it like a negative area. And it's a negative area of 2 that cancels out this positive area of 2 of the blue triangle. So since they cancel out, that's going to end up giving us an area of 0, right? Because the areas cancel out. So that's going to be g of 4 equals 0. Okay, g of 6 equals what? Well, it's really helpful, and the teacher knows this, which is why you're being asked to answer these questions first. So we could take into account that so far we have an area of 0, but what about the new area here called g of 6, where we take into account not just the blue triangle, not just the yellow triangle, but now we're taking into account this other triangle, which we could shade in with green. Now we know that the blue and the yellow ended up canceling each other out. So now when we quote-unquote add this extra area on top of what we already have, what we're going to have is a negative 2, right? Because the area of this green triangle is negative 2. And when we add negative 2 plus what we already had, we're going to get a negative 2, because what we already had was 0. So when we add negative 2 on top of that, that's going to be negative 2. All right, so you just have to kind of keep track of what's come before, what came before. All right, and then we have g of 8. Well, so far, once again, keeping track of what we have so far. So far, we have an area of -2. So g of 8 is asking us to take into account what we have before, and then we are adding this, right? This new triangle, which we could now shade. I'll shade it in red. Shading the new triangle in red. Well, guess what? As my student at home probably can see, this darn red triangle cancels out this green triangle. These two triangles canceled out each other. So everything cancels everything else out. So therefore we have, once again, 0 as the sort of cumulative area under the curve. And we know that we're looking for the cumulative area under the curve because x is 8, and they're asking us to consider the x values from 8 to 0. So that's considering all the x values, this whole domain of values from 8 to 0. And literally the area under the curve cancels out within that domain. All right, so then we have the next one, which is g of 10. And that's asking us to take into account everything that's come before, but now we're focusing on the new section. And the new section is this section right here, which I shall label in yet a, well, I'll label it in black actually. They want us to take into account this black section right now. Now, so far we know that that right there is going to be an area of 4 plus this black section right there. So that's going to be an area of 4 plus half of a block. We know that a single block is 4, half of a block is 2, so that's going to be this full block of 4 plus 2, and that's going to be 6. Now, it's going to be 6, this whole black section is 6, on top of what we already have. So therefore, we already have 0, right, because all of this stuff canceled. So it's going to be 6 plus 0. That's going to end up becoming 6, because 6 plus 0 is 6. All right, let's see. G of 12. G of 12. Well, that's once again asking us to take into account what has come before, and what has come before is 6. We have a total of 6. All the way from 0 to 10, we have the area under the curve, the cumulative area under the curve is 6. So now we're being asked to take that into account, plus this extra section here. I'm going to label this extra section in purple. Okay, I don't often bring out the purple, but I think it's worth it. This extra section here in purple, let's take a look at it. Well, it would be one block of 4, plus another block of 4, which is a total of 8, plus this triangle that has an area of 2. So one block of 4 plus another block of 4, that's 8, plus 2 is 10. So therefore this whole purple section has an area of 10. So it's going to be an area of 10 on top of the total cumulative area that we've already calculated before. The total cumulative area that we've already calculated before is 6. So now we're going to add 10 on top of that 6. So that's going to be 16. That's going to be 16. Okay. So that's how you handle that. With each successive thing that they ask you for, you take into account what came before. Now, you might even want to draw a graph and color code it or shade it in with your pencil, find out which shapes are canceling out which other shapes, etc. But g of 12 should be 16. Okay, so we're going to estimate g of 14. So when it comes to estimating g of 14, how do we continue to apply the same sort of strategy? We would end up figuring out, okay, well, what is this empty triangle here? But the teacher is purposefully presenting a graph that has a slight curve here. And I think the idea there is to just highlight the fact that we are indeed estimating at this point, whereas this might be a little bit more of a precise calculation due to the fact that this part of the graph is a straight line, this part of the graph is a straight line. We now have a little bit of a curve going on, so now we've sort of officially entered the land of estimation. Okay. Now, another thing worth noting, of course, is the fact that there's this mention of use the midpoint to get the most precise estimate. I'm going to assume that the teacher therefore wants us to use the midpoint rule. So let's dive into using the midpoint rule for this. Now, the way that I'd like to present this is visually, okay? So essentially what we're being asked to consider are rectangles of equal width. I'll present a visual way first and then an algebraic way. So imagine, we want the area under the curve and we want it all the way up to 14, right? So we want to consider rectangles of equal width. So that's for sure. So we could have a rectangle here. Each width could be 2, right? Each width could be 2. But the question is, what's the height of the rectangle going to be if we're going to use the midpoint rule? So here is us using the midpoint rule. Here's a rectangle, and you want it to have a height such that the midpoint of the rectangle meets the graph. Okay, so let's zoom in super close. The midpoint of the rectangle meets the graph. That's the midpoint rule way of going about the area under the curve. So we have another rectangle right here that has a width of 2, sure, but as far as the quote-unquote height, it is such that the midpoint of the rectangle meets the graph there. So I'm going to put a little red, or I'll put a little blue dot where the midpoint of the rectangle meets the graph. Okay, the midpoint of the height of the rectangle. Not this corner of the rectangle, not this corner of the rectangle, but the midpoint of the rectangle. Similarly, we would have another rectangle with a width of 2 right here, right, with that little midpoint of the rectangle meeting the graph there. And all the way down the line, we have a width of 2 here, right, with that touchstone right there. We have a width of 2 here. This rectangle goes all the way up like that. And that's the point of contact right there. This rectangle goes all the way up to this part. The point of contact being here. And here's kind of the moment of truth, really, where it's like width of 2, and the rectangle goes all the way up. Actually, it looks like it goes all the way up, same height as that last one, doesn't it? Because the midpoint really would be right there, just visually, you could see that. So that's what it looks like visually when you use the midpoint rule. If you want to use, okay, so let's stick with the visual. So sticking with the visual, you would just basically figure out the area of each rectangle and then just add it all together, right? So the area is going to be width times height. Okay, width times height. And how many rectangles do we have? We have 1, 2, 3, 4, 5, 6, 7, right? So we have 7. I'll get into the more like algebraic, purely algebraic way of doing this in a second, like I said, but we're going to add the area of 7 triangles. So sticking with the visual approach, we're going to have the area of one triangle plus the area of another plus another, and it's going to be 7 total rectangles. So I'm just going to kind of get this over with. Here's the 7 rectangles, and we'll even like label it R1, R2, R3, and so on. R4, R5, R6, R7. And moving on, so the area of this first one, well, that's definitely 2 times, looks like a height of 1, doesn't it? So that's going to be 2. Bam. The area of the second one, same size. This one's going to be -2. -2. The area of the next rectangle, that's going to be also another -2. The area of the fourth rectangle, well, that's going to be 2 times the height. And the height is 1, so that's going to be 2. All right, in case that's not clear, let's blow this up. We are looking at the area of this fourth rectangle. It's 2 by 1, so that's going to be 2. The area of the fifth rectangle right here, well, that's definitely going to be 2 times whatever the height is. Looks like the height is 3, yeah? The height is 3 because that's 2, and then up a half of a block is going to give us a unit of 1 on top of that too, so that's going to be 2 times 3, also known as 6. Looking at rectangle 6, which is right here, that's going to be 2 times whatever the height is. It looks like the height is 5 right there because this is a height of 2, this is a height of 4, and this is halfway up, so that's going to be an additional 1. So this rectangle right here has a height of 5, so that's going to be 2 times 5, which is 10. And this rectangle is the exact same size, right? So that's going to be 10 also. So that is a visual approach to using the midpoint rule. 2 plus -2 is 0, plus another -2 is -2, plus 2 is 0. So all of this cancels out in the same way that the triangles had canceled out before. All of this cancels out, but we're left with 6 plus 10 plus another 10, and that gives us 26. So unless I made a careless mistake, using even the midpoint rule, that should give us 26. Now, let's say you want to use more of an algebraic way. That would look like the following. The reason I do the visual way, for the record, before I do the algebraic way is because the visual way, I think, is a better way to understand what the heck is going on in reality, what even the algebraic way is sort of pointing to. And the algebraic way would be something along these lines, for the record. It would be f of x dx is approximately, this is an approximation, delta x times this ridiculous thing. So for my student at home, if your teacher has not taught this, don't worry if you don't understand this right away. I'm going to translate this in a second. So what does this even mean? Well, basically, the first question you should be asking yourself is, what does delta x mean? Now, I'll just tell you that delta x means the width of each rectangle. So basically, in a sense, you want to, if you're going to use the midpoint rule to find the area under a curve, you ask yourself, okay, you know, what is the width of each rectangle going to be? And in order to know that, let's say you got a curve, you need to know how many rectangles you're dealing with, right? You need to know how many rectangles you're dealing with, and then you take into account the range. In this case, it's from 14 to 0. And then you divide by that many rectangles, and that gives you the width of each rectangle. Okay, so I'll just tell you what delta x is in algebra language. Delta x is, therefore, b minus a all over n. Now n stands for how many rectangles, how many rectangles you want to use. All right, and when you're taking into account b, that is the top number on the integral, and this is the bottom number on the integral. And what I mean by that is, if you have an integral of like f of x dx or whatever, the b would be here and the a would be there. Okay, so it's going to be b, this minus this, all over the amount of rectangles you want to deal with, and that will give you the width of each rectangle. Okay, so that goes here, and basically what you're doing here, I know this looks like a bunch of craziness, and at a certain stage you're going to be able to decipher this skillfully, but I'll just tell you right now, this means sum. Okay, this is the sum of stuff, right? But this is the sum of all the heights of each triangle. That's really what it means. So in other words, really what this means is this: the width of each triangle times the sum of all the heights. All right, but it's the height of the rectangle at the midpoint. That's what this little thing means. This part right here means you're taking into account the midpoint of the rectangle. Okay, so in this case it would be, taking into account this whole scenario here, like algebraically, it would look like the width of each triangle is 2, clearly. But then it's going to be the height of, looks like we had 7 rectangles, right? So I'm actually going to write 7 heights here. And height's denoted by, f of whatever. So that's 4, so we need 3 more. And finally this one. So all of this shenanigans, f of this shenanigans here, means the midpoint between the two corners of each rectangle. So, like for example, on the first rectangle, the width is 2, which is, by the way, denoted here. But the x value that goes here should be somewhere in between 1 and 2, right? So, or 0 and 2, I should say. So that's going to be 1, okay? We're taking into account the x value of 1 right there. And over here, we're going to take into account the x value of 3, right? Do you see how the blue dot corresponds with the x value of 3? So in other words, the x values for each of these is going to correspond with the x value of each blue dot. That's another way of looking at it. All right, so hopefully that makes sense to my student. Let's put in those x values, and since the x values correspond with the blue dots, I'm actually going to write it in blue. So that's going to be 1, 3, 5, 7, 9, 11, and 13. And yeah, that's the algebraic way of doing it. Okay, f of, whatever the x value is, the x value is the x value that corresponds with the blue dot, and we go all the way across. That's going to end up becoming 2 times 7 different heights, which I'd rather just get this over with. That is 1, 2, 3, 4, 5. We need 2 more. Those heights are, let's see, what was it? We had 1, we had -1, we had another -1, we had another 1. The height for And by the way, this corresponds with that, this corresponds with that, this is going with that, this is going with that, this one goes with that, this one goes with that, and this one goes with that. So when it came to this one, when x was 9, the height was 3. And when it comes to f of 11, when x was 11, the height was 5, right? And the height was 5 over here as well. So that's the more kind of like algebraic way of doing it. If your teacher ever wants you to represent, you know, the formula and kind of translate the formula into algebra, it would look something like that, where it would end up being, you know, again, the width of all the triangles, the width of all the rectangles, times the sum of all the heights. Well, all the heights are represented here. The sum of all the heights would end up becoming the following. So we have 2 times, canceling, 8 plus 5, that's 13. And that's going to give you 26, all right? So that is a quick overview of what it might look like if you use algebra instead of the purely visual approach. Okay, so let's move on. Now they want to know, where does G have a maximum and minimum value? Well, once again, G stands for the area under the curve. So in other words, like, let's focus on the maximum first, okay? Like, when was the area at its greatest, right? When was the area at its greatest? Well, the area was at its greatest here. And here's how I know, because all the area canceled itself out, you know, around here. Let me just get rid of these, actually. All of the area here and here and here, well, all this stuff, like, got canceled out, didn't it? So it was like 0 here, right? So it was 0. It only became positive, really, cumulatively positive, once we got past 8. That's when we had 0, and then all of a sudden we have an area of, was it 4 plus a half? So it's 5. We have an area of 5 right there. And then we have an area of, looks like it's 10 right here, because we have 2 blocks totaling 8, plus a half a block totaling 10. And then on top of that, I mean, we had even more area underneath whatever this is, right? So really, when x is 14, that's when the area under the curve was at its peak. That's when the area under the curve was at its highest, right? And seeing as how it's most helpful to think of g of x as representing, you know, as being a function representing the area under a curve between 2 different x values. That's the best way to think about the maximum, in my opinion. All right, so just keeping all of that in mind. Therefore, the maximum should be at 14. But then the question is, where was the area at its minimum? Big question mark there. Well, the area was at its minimum. Let's see. We had the yellow triangle here. That's a positive area. It got canceled out here. So the area is at 2 in that moment. Actually got canceled out here, pardon me. So the area is at 2 in that moment. And then there was another negative area, quote unquote, on top of that, called -1, right? That's when the area was at its lowest, because it becomes positive again here. There was one moment where the area was actually negative, right? And the cutoff point where the area was actually negative will be denoted in purple, right? And that corresponds, it looks like, with the x value of 2, 4, 6, right? So that's the x value of 6 right there. In that moment, the total cumulative area under the curve was negative. That it was at its lowest, because the area under the curve when x was 2 was 1. The area under the curve when x was 4 was 0 because this negative area canceled out this positive area. But then the area under the curve when x was 6 was actually a negative 1 because when x was 4, we had a cumulative area of 0. And then on top of that, we're quote-unquote adding this green triangle. The green triangle has an area of negative 1, so that was negative 1 on top of the 0 that we already had. So the area when x was negative 6, from 6 to 0 was a cumulative total of negative 1. Then after that, it became positive again, or at least became 0, or it went up to 0 here. So once we got up to this triangle, the area started growing again, right? It actually cancels out. It becomes 0 there, and then it becomes more than 0 here, and then more than 0 here, and then even more than 0 here, of course. So anyway, it was at its lowest when x was 6. So I hope that makes sense. So the minimum was when x was 6. So I'll rewrite this. So its maximum is at 14, and the minimum was when x was at 6. So again, unless I made careless mistakes, that's the answer to this last one. Anyway, so for my student at home, please text me with any questions. And for those of you watching, if you have any questions or comments, even if I made a careless mistake and you want to point it out, just put it in the comments below. And I hope you guys understood that, and I will see you next time. Take care.